theoretically I have a shorter talk, so I guess this might work out for the last day of the talk, or last talk of the day. Okay, so I wanted to kind of tell you about this paper that we published with Tal and Guy last year on exactly solving marginal map. Which I guess the query marginal map kind of came up a couple times during the workshop. So the particular reason I wanted to kind of tell you about this solver approach is it has slightly a different flavor than kind of the exact algorithm by like feed forward evaluation that we've seen more in the workshop. So we've already seen this a couple of times, but just to make sure that we're all on the same page. So to define marginal map, basically the query is that if you have a distribution over a set of variables x, we want to find the state over those some set of query variables to maximize the marginal probability. And you could do this with some evidence given optionally. Doesn't matter too much. Really, the idea is the key thing is that you need to you want to maximize some marginal probability, so you need to sum out some latent variables or some hidden variables. Okay? Essentially, this is kind of you can think of it as like a two-layer of queries. You're trying to compute the map of some marginal distribution. So this makes it, in general, NP to the PP hard for graphical models and so on. So now let's consider the case where our distribution P here is actually given as a probabilistic circuit. So just to, I'm sure this is probably like boring for you at this point, but just to make sure we're absolutely all on the same page, right? So if the circuit that's given is smooth and decomposable, we know that we can compute marginal probabilities in linear time just by feed-forward evaluation, and we can compute marginals for any arbitrary partial assignments to arbitrary subsets of your variable. And then if we additionally have deterministic sum nodes, then we can also compute map or MPE tractably. Okay? So if you are trying to maximize over all set of variables in your circuit, you can do this tractably with smooth decomposable and deterministic pieces. The problem is even if we can compute marginals and map tractably, so even for smooth decomposable and deterministic circuits, computing marginal map query is still NP hard. Okay? And kind of the intuition of why that is basically we're trying to maximize over some marginal distribution. So essentially, we need this. We need the circuit that's going to represent that marginal distribution to still be deterministic, which is in general not true if you're given some deterministic circuit. So how we compute marginals is, for instance, let's say your query variables are just x1 and x2 in this circuit over 3 variables. How you compute marginals is just to replace all of these leaf nodes that you want to sum out with ones. Okay? In this case, they just all get multiplied into 1, so they basically just disappear. So in this resulting circuit, now this is no longer deterministic, right? So if you look at this sum node for a value, of x2, so if x2 is false, both of these inputs to that sum node will be non-zero. So this is no longer deterministic, and we cannot just linear time compute the marginal map query for this query set. Okay, so what can we do? Well, we can, of course, try to find the structural constraints, the circuit constraints that will let us compute marginal map in linear time, right? And we already saw one example of that in Rina's talk, where if you have AND or search with a constrained pseudo tree, basically if you have all the map variables or query variables appearing at the top of your circuit, then you can compute marginal map exactly in linear time. There's slightly general definition that basically just says after you marginalize out some variables, the resulting circuit is deterministic. So you can just call that like marginal determinism or Q determinism. This is still very hard to enforce. I think Benji might be telling you more about this on Friday. So this property also shows up for queries other than marginal map. The point is to enforce these constraints, because once you enforce them, you can compute this NP-hard query in linear time. Actually, trying to do that is hard. Your circuit might, your circuit size might blow up. You may end up with exponential size. And also another point is that if you have a circuit, you enforce this constraints for a particular marginal map query. And then let's say you want to compute another marginal map for a different set of query variables, then you need to go through all of that process all over again. You have to change your circuit to conform to that different constraint. Right? So that's very expensive. So another alternative is to keep the circuit as is and then perform search on top of it. This is an optimization problem. You can perform search. So what we looked into is essentially instead of kind of in one go enforcing this hard constraint, we're trying to keep upper and lower bounds on the marginal map probability while transforming the circuit iteratively. And in the end, we will end up with a circuit that actually is tractable for marginal map. The kind of catch that's hidden is that you may change the distribution as you're changing the circuit, but the guarantee is that we will not change the marginal map solution. So for this problem, we can actually do this iterative transformation, changing the distributions, because you will still output the right answer. Okay, so as a starting point, let's first look at what the easy way to first get a lower and upper bound for a particular marginal map query. So in the search for marginal map paper that I mentioned in the previous slide, there's essentially an algorithm to get an upper bound on the marginal map through a single feed-forward pass. This is basically the same algorithm that would get you the marginal map solution if you started with a constrained circuit. If you just run that algorithm on a circuit that's actually not tractable for marginal map, what you end up with is an upper bound. Okay? And I'll actually show you a bit of an example of that later. And then as for lower bound, because this is a maximization problem, you can just choose any assignment Q and then use its marginal probability as a lower bound. So in practice, for example, you can compute the full assignment at MPE, just take the assignments to the query variables, and that tends to work okay as a starting lower bound. So the question is, how can we tighten these bounds, right? Starting from these, how can we make them better? And the goal is to tighten the bounds until both they converge to the exact marginal map solution. So that's exactly what we're going to do by transforming the circuit iteratively. So the main idea that we use to come up with iterative transformation is to notice that when you're computing the marginal map probability, not all parts of the circuit are actually relevant. So what do I mean? Let's take this example circuit, and then let's say we're computing this marginal probability. Right? So we have a circuit over 3 variables, computing this marginal probability given a partial assignment to 2 variables. So in this case, only the circuit that are highlighted in blue is actually relevant. So if you see, so all the other ones that are not colored, all the black edges will either propagate 0 or will get multiplied with 0 at some point. So it doesn't actually contribute anything to this marginal probability. So for example, we're given x1 is 1, x2 is 0. So this one will just evaluate to 0. So it's not relevant at all. Over here, these may evaluate to something non-zero, but then in this side, because x1 is given as 1, it'll get multiplied with 0. So all of this subcircuit over here is also irrelevant for this particular partial assignment. And for this particular example circuit, it turns out that this assignment that we were looking at is actually the marginal map solution. Right? So which means if we were to get rid of any edge that's not colored, that's any black edge that's not highlighted, if we prune those, it's not going to actually affect your marginal map solution. Right? So for example, in an extreme case, if we just look at this blue colored subcircuit and then ask for the marginal map or ask to compute marginal map, you get back the same answer. So now the question boils down to: can we actually efficiently identify which of these edges we can prune? Can we identify which of the edges will be irrelevant for your marginal map solution? So for that, what we're going to do is define a bound on every edge that we say if this, okay, let me just go through. So for every edge, what we're going to say is what's the largest marginal probability you can get from an assignment that actually uses that particular edge. Basically, for each edge connecting node and C, we're going to define a bound that essentially is an upper bound for a different marginal map query, if you will, where you're trying to maximize the marginal probability over a smaller set of assignments, where that set is defined as just the partial assignments that actually activates the edge, meaning that actually propagates something non-zero on that edge. So in the earlier example we were looking at, so this partial assignment that we were looking at appears in this set C for all the edges that are highlighted in blue, and then it will not appear in the other edges that are not highlighted. Or another way of looking at it is, let's say we're looking at this this set C for just this orange edge here. Right? So we're asking which assignments to variables x1 and x2 actually activate or uses this edge. In this case, that just corresponds to setting x1 to 1, and value of x2 can be either. So in this edge, we'll have these two partial assignments appearing in that set, and the goal is to compute a bound that says that will return the larger or maximum probability on this edge, so larger marginal probability between these two assignments, if we're looking at this particular edge. So if we have such a bound, then given any lower bound on your marginal map probability, you can say if this bound does not exceed that lower bound, we can see if we prune that edge, right? Because this just says this is a lower bound on your solution, and you're saying assignments that use that edge is not going to have a marginal probability larger than that lower bound, meaning none of those can be a marginal map solution, right? So we can get rid of that edge. And we show that for So if your input is a smooth and decomposable circuit, we can compute these edge bounds for all edges in your circuit in a single feed forward and then a backward pass, so in linear time. I'll kind of give like a high-level idea of that bound algorithm with kind of an example and pictures essentially. You can also talk about it more formally offline if anyone's interested. But basically, what we'll do is first start with the feed-forward algorithm that I mentioned that will get you the upper bound on the marginal map solution. Okay? And how it works is essentially you identify these. So okay, here the setting is still the same. So here, say the query variables are x1 and x2. So now we're going to look at the sum nodes and see which ones are actually Q deterministic. You can just think of them as like a decision node on a query variable. So so for any of those sum nodes that split on a query variable, what we'll do is actually turn that into a max node. So here we choose the max between these two. That's just 0.9. Do the same thing here. So choose the maximum between the two. And then for the other ones, it's just business as usual. Compute products and weighted sums. So compute the weighted sum here again, and then at the top here. So this is another Q deterministic sum node. This is basically a decision node on x1. So at that point, we also take the max between here. Essentially, take the max between 0.93 times 0.6 and 0.84 times 0.4. Okay. So this is our starting upper bound on the marginal map solution. And then now what we'll do is, starting from that bound, go backwards, so top down in the circuit, tightening the edge bound. So tightening the edge bound every time we encounter this Q deterministic or decision node on the query variable. And sort of the intuition of what the bound is trying to do is, for example, okay, for example, if you are trying to get the edge bound on this or on this edge right here, what this value is trying to or what this value will give you is essentially, imagine this sum node only had that edge as an input. So imagine this edge didn't exist, and then say you run the same feed forward algorithm to get the upper bound. So in the previous example, the upper bound we chose here was coming from this edge. So if you get rid of that and then run the same upper bound or feed forward upper bound algorithm, you're going to end up with a smaller value because you're going to propagate a value from another one that was not chosen in the max. So so that's kind of the intuition of what each of the edge bound is trying to say is, if you are forced to use that edge, what would the upper bound have been? And kind of the key part of the algorithm is, instead of actually removing an edge and running the feed forward algorithm and doing that over and over again, we can actually use the cached value from the previous feed forward pass to get that edge bound for all edges in one go. So that's really all that's happening. So if we don't see a Q deterministic sum, we just kind of propagate the values from parent to children. And then down here, do the same thing. So see on this edge, you can tighten the bound by essentially looking at the cache values and doing some subtraction in a careful way that still guarantees you that this is an upper bound. So if we computed this kind of edge bound, and let's say you are using some partial assignment to give you a lower bound on your marginal map. So now you have the lower bound, and then you can look at the circuit and say, oh, so these two bounds have values smaller than the lower bound. I can get rid of it. So make the circuit slightly smaller. Of course, the catch is this backward pass isn't going to prune every edge that you possibly can. So this is not going to magically solve marginal map in one go. So what we have to do is iterate between pruning the edges as much as you can, and then another transformation called split, basically, which is trying to also introduce more Q-deterministic subnodes, which gives you more opportunity to tighten your bound. And split is nothing but basically Shannon decomposition or introducing a decision node. So if you're splitting on variable x1, you just introduce this decision node on x1 and then connect the subcircuits, each of which are kind of conditioned on the two values of x1. So every time you introduce this split at the root node, that's going to tighten your bound. And in this iterative approach, we are splitting on one variable at a time. After we split on all of the query variables, then you end up with a basically you end up with the constraint structure where you have all the map variables at the top of the circuit, right? Which is the case where we know we get the exact marginal map solution. So you basically we know the number of iteration is going to be at most the number of query variables you have. So kind of course, this is still solving an NP hard problem, even though in an iterative way. So the catch is every time you do this split, you may double the size of the circuit, right? But what we saw in practice is in a lot of cases, pruning actually gets rid of a lot of the parts of the circuit. So even though you may double the size, in the next kind of iteration, you may prune a lot of the lot of parts of the circuit. So then you can double decrease it again, double decrease it again. So this is kind of one example run of the iterative solver, and this kind of looks like a typical run, really. So what we see is, here you start with size something like a little over like 8,000. So initially, when we're doing a lot of splits in the variables, we do see that the circuit size increases. But as we continue and tighten the bound, we can prune more and more parts of the circuit. And at the end, what we actually end up with is even smaller than what we started with. And this is kind of a visual representation of what's happening in each iteration. Is we starting from some lower bound and upper bound and iteratively tightening it until we end up at the exact solution. So yeah, and so we compared with essentially a search-based solver for map and MPE on some perfect networks, which are also smooth and decomposable circuits. And especially on these kind of larger data sets, we saw that the search algorithm couldn't converge. It was essentially like timing out, and we could solve almost all of those cases, right? So at least on this benchmark, pruning seems to work well enough to keep the circuit from blowing up beyond control. Okay. Yeah. So I'll conclude there. So essentially, yeah, the main idea was that we can do this iterative circuit transformations, going back and forth between pruning and splitting to tighten upper and lower bounds on your marginal map query, right? And even though each split might, in the worst case, double the size of the circuit. It seems like, at least in the benchmark bit that we tried, pruning seems to work pretty effectively. Although, it would be nice if we can provide any guarantees. This was also using kind of a heuristic that I, kind of came up with. Seems to make sense intuitively. I just tried a few and seemed to work well. Of course, can be improved. Yeah, and just to mention, I presented this as a marginal map solver. Of course, we're starting. You can give it a non-deterministic circuit, so you can solve for example MPE for some project that works, or marginal map. But yeah, all the same. And maybe one question is, can we actually generalize this approach to get bounds for other queries that also seem to require determinism to compute tractably on a circuit. Also, going with the recurring theme of the program, can we generalize? Can we give it like a semi-ring treatment? Here, I think the one point is that to tighten these bonds, we needed to basically do subtraction to tighten the upper bond going from top to bottom. But then these values, it's not exact subtraction we need. It's really, we need to find some value that satisfies some inequality. So maybe like modus is okay. There are probably like experts who can tell me here. But yeah, I think that's it. Thank you.
Hi, thanks for the talk. In your experiments, we can see that the lower bound stabilizes very quickly. Is it an artifact of the implementation or just the example? Or?
That's actually an observation that I kept seeing actually quite often. So the lower bound I was using is essentially what I mentioned earlier of like computing MPE and then reducing it to the query variable set. That seems to give you a pretty good lower bound, at least it does seem to stabilize quite early. I don't have a good explanation for that. I don't know if that happens like beyond these benchmarks, but it is actually something we noticed, at least on these 20 data sets.
Thanks.
Yeah, thanks. Nice work. Does this carry over to continuous PCs as well? Like if I have Gaussian leaves or whatnot?
Yeah. So I think if you're given deterministic circuit, then you have like leaves with maybe like truncated support. In that case, I think you can use that to introduce these like Q deterministic nodes at the top. So I think you can use those to split, right? Otherwise, I think if you try and split, I need to think if you run into problems like renormalizing after you like introduce this like truncated Gaussians that didn't occur in your input circuit. But at least for if you're starting with a deterministic circuit, I think you can pretty much apply that.
Okay, and if I start with something like Gaussian leaves, then it's probably doable, but like a little bit finicky, right? So
yeah, then you have to like think about like how I'm going to split, like how do I want to split the support, because you have to introduce these you have to introduce some Q deterministic some nodes at some point, right? Because that's the only time you actually tighten the bounds.
Can you say something about the data sets that you are using? Are those graphical models? Are those circuits? What is the input?
No,
what is the input?
So these were all like discrete variable data sets. So the input to the algorithm was basically we took these data sets and then learned a smooth and decomposable, in this case actually I think structured decomposable circuit. So we learned circuits, and then from that, starting from the circuit, we run the search and our.
So the input is a circuit.
Input is a circuit, yeah.
And and the data set, when you are learning the circuit from the data set, do you assume a structure, or you learn both the structure and the parameters?
We learn both the structure and parameters from data.
And you are guaranteed to have a circuit that will be, can be in memory, so it's bounded. So if it was a graphical model, not necessarily you can have this as a starting point, right?
Yeah, that's true. So if you're starting from a graphical model, if you're trying to compile exactly, the hard part might be actually getting the circuit. In this case, at least you're not compiling to a constrained circuit, so we just need smoothness and decomposability. So we may be able to compile, more models than if you were to try to compile it into a constrained circuit. Right?
Okay, thank you. And just one more question. When you are comparing with a search algorithm, which search is this? Something in the literature, or you implemented it?
Yeah, this is from like a sum product network literature. So this is they had different heuristic-based search for both MPE and marginal map on smooth and decomposable PCs.
Okay, thank you.
Yes, thanks for the talk. Nice work. My question is, if I understand correctly, you're running a branch and bound. So one of your operations is a branch, the other is a bounding, and then you put them back into circuit, which means you can still do both things but keep them in a single circuit. My question is, why, instead of just doing the branch and bound separately and then keep the small circuits reducing as you keep doing the branch and bound?
So we're not explicitly doing branch and bound, if you will. So it's a little weird to think about. But so by splitting and then introducing another like split node at the root and so on, we're kind of almost like building a search tree like bottom up, if you will. So what you end up with at the end, you do end up with something that looks like a search tree, but we're not really explicitly doing search
I think it's very
trees.
explicit. I mean, this is just a branch and bound, right? Because you keep the two new circuits. So my question is, why to put back in the circuit instead of keeping them separately and, let's say, queue them to process? My question is, isn't the same, or you're getting something by keeping them into a single model?
I think so.
I might be missing something. We can discuss.
Yeah, I think what we introduce, there's a split decision nodes we introduced at the top. So the ones that we introduced, I mean, really the main thing is sometimes down here, down in the subcircuits, you may have like shared subcircuits, right? So you don't have to like keep track of different. This is like keeping track of like different branches in parallel, but also with like shared subcircuit. That makes sense.
We can show
We can.
A quick one. Have you tried also a comparison against the PSDD with the constrained V3? And if so, the problem is that the circuit becomes too large, or just perform poorly?
Yeah, usually the problem is that it does become too large. If we're learning, we can give it we can give it a constrained V3, but then so in the learning part, then usually the issue is that you end up with something that's like less expressive. You don't get you get like lower likelihood on the particular data if you're learning, and then if you're trying to compile, then of course the compilation part goes
just for my understanding, but the constraint is like the Q variables are on one side and the other variables is something like
basically.
that. Okay.
Other questions?
Yeah, so following on Rena's question, so what are the queries? Do you just solve mmap for each variable? So for your experiments, what are the queries?
For these, so here basically this is kind of the percentage of query, hidden, and evidence, or query, evidence, and hidden variables that we have. So according to those percentage we kind of randomly sample. So for example, we'll randomly sample like 30% of the variables as the query variables. So these are on, average on some random instances of marginal map.
And what happened for that case that you didn't finish? I see there's a 9 out of a bunch of
There
things.
are a few that we
Okay.
couldn't finish. Yeah, so there what's happening is usually the circuit does blow up.
I see.
Any other questions? So I actually have a question. I think like the crucial step is identifying the Q deterministic sum nodes, right?
So so partially we kind of cheat that we are like introducing these decision nodes at the top, and at the
Right.
bottom we have something that can essentially find not all Q deterministic, but some Q deterministic nodes, even though maybe they're not exactly decision nodes.
Okay.
So we have something in between that's actually you can do a first linear time preprocessing to kind of designate those nodes. And then continue.
I assume that is somehow easy to do, right?
Yeah, I mean, if they're decision nodes, then we can definitely
Right.
find them pretty easily, and then you can also find some extra ones. But yeah, if your circuit is such that it's very hard to find any Q deterministic node, then what happens is until you do enough splits, you basically wouldn't prune anything.
Right. Okay. No more questions?